Hi, this is Amna, optometrist from Global College of Allied Health. Today I am going to discuss about the topic of cornea. The cornea is a transparent avascular watch glass-like structure. It forms the anterior 1/6 of the outer fibrous coats of the eyeball. The dimensions. The anterior surface of the cornea is elliptical with an average horizontal diameter of 11.75 mm and the vertical diameter of 11 mm. The posterior surface of the cornea is circular with an average diameter of 11.5 mm. The thickness of the cornea in the center is about 0.52 mm, while at the periphery it is 0.67 mm. The radius of curvature. The central 5 mm of the cornea forms the powerful refracting surface of the eye. The anterior and posterior radii of curvature of the central parts of the cornea are 7.8 and 6.5 mm. The refractive power of the anterior surface of the cornea is about plus 48 diopter, and that is of its posterior surface is about minus 5 diopter. Totally, the net refractive power of the cornea is about plus 43 diopter, which is the 3/4 of the total refractive power of the eye, that is 60 diopter. The refractive index of the cornea is 1.37. Histologically, the cornea consists of 5 distinct layers from the anterior to posterior. These are epithelium, Bowman's membrane, substantia propriae, that is stroma, Racemets membranes, and endothelium. This is a microscopic structure of the cornea, consists of the layers epithelium, Bowman's membranes, stroma, Racemets membranes, and the last layer is endothelium. The first layer, epithelium. The corneal epithelium is of stratified squamous type and become continuous with the epithelium of bulbar conjunctiva at the limbus. It is about 50 to 90 mm thick and consists of 5 to 6 layers of cells. The deepest layer is made up of columnar cells. Next, 2 to 3 layers of wing or umbrella cells, and the most superficial 2 layers are of flattened cells. The corneal epithelium sheds at the regular interval and it is replaced by the growth from its basal cells. It is estimated that the entire epithelium is replaced in a period of 6 to 8 days. Some important features of the various layers of epithelium are that is basal layer comprised of tall columnar polygonal shaped cells arranged in a palisade-like manner on the basement membrane. It forms the germinal layer of the epithelium, which undergoes mitosis to produce daughter cells, which are pushed anteriorly to the wing cell layer. The basal cell has no oval nucleus and its cytoplasm contains few organelles. Some tonofilaments, free ribosomes, rough surface endoplasmic reticulums, and occasional Golgi bodies are seen. The mitochondria are small fuse, suggesting a low aerobic oxidations and more dependence on the pentoshunt for metabolism. The basal cells are firmly joined laterally to the other basal cells and anteriorly to the wing cells by desmosomes and maculae occludens. These tight intracellular junctions account for the epithelium transparency as well as a resistance to the flow of water, electrolytes, and glucose. Its barrier functions. The basement membranes of this basal cells is positive structure. Posteriorly, it blends indistinctly into the Bowman's membranes. Anteriorly, free adhesions are formed between it and basal cells by the filament extending from the later. In fact, the basal membrane is of utmost importance in the epithelial cell adhesions. When abnormal, it is associated with recurrent erosions and epithelial defect. The wing cells form 2 to 3 layers of the polyhedral shaped cells. The nuclei are flattened shapes parallel to the surface and cytoplasmic organelles decrease as compared to the basal cells. They are attached with the basal cells posteriorly and other wing cells laterally and anteriorly. The flattened cells constitute two most superficial cell layer. These are cells are long and thin with flattened nuclei. The desmosomal attachments and maculae occludens are more numerous in these cells. Further zonules occludens are seen in lateral cell walls are found in the layer only. The anterior cell wall of the superficial cells has many microvilli, which plays an important role in the tear film stability. The second layer, which is named as Bowman's membrane, this layer consists of acellular mass of condensed collagen fibrils. It is about 8 to 14 μm in thickness and binds the corneal stroma anteriorly with the basement membrane of the epithelium. It is not a true elastic membrane, but simply it consists of a superficial part of the stroma, which shows considerable resistance to the infections and injury, but it is once destroyed, it does not regenerate. The third layer stroma, which is known as substantia propria. This layer is about 0.5 mm in thickness and constitutes most of the cornea. It consists of the collagen fibrils and the cells embedded in the hydrated matrix of the proteoglycans. The lamellae, which are arranged in many layers. In each layers, they are not only parallel to each other but also the corneal plane and becomes continuous with the scleral lamellae at the limbus. They vary in the dispositions according to the area of the cornea. They have the oblique orientations in the anterior 1/3 of the stroma. In the posterior 2/3 of the stroma, the alternating layers of the lamellae are at right angle to each other. The studies using X-ray diffraction techniques have shown that the parallel arrangement of the central corneal fibrils extends to the periphery, where the fibrils adapt to the concentric configurations to form a wave at a limbus. This imparts considerable strength to the peripheral cornea and permits it to maintain its curvature and thus its optical properties. Previous studies have shown that the corneal fibrils running in two preferred orientations in the central cornea bends as they approach the peripheral cornea to run circumferentially and form the peripheral collagen ring. The parallel arrangement of the lamellae in the cornea allows an easy interlamellar dissections during the superficial keratectomy and lamellar keratoplasty. The peculiar arrangement of the lamellae has also been implanted to the corneal transparency. It is believed that the cells produced ground substance and collagen fibrils during the embryogenesis and after the injuries. The wandering cells of the stroma migrates from the marginal lobes of the corneal blood vessels. The fourth layer is Descemet's membrane. It is a strong homogeneous layer which binds the stroma posteriorly. It represents the basement membrane of the endothelium from which it is produced. Through the elasticity, it is one of the physical characteristics. It is made up of collagen and glycoproteins, which has no elastic fibers visible by the electron microscopy. Its thickness varies with the age, being 3 μm at birth and 10 to 12 μm in young adult. It is very resistant to chemical agents, trauma, infections and pathological processes. Even the whole of the stroma is legged off. The Descemet's membrane can maintain the integrity of the eyeball for a long period. Further, unlike Bowman's membranes, when destroyed, it can regenerate. Normally, it remains in a state of tensions and when torn, it curls inwards on itself. In the periphery, it appears as a end at the anterior limit of the trabecular meshwork at the Schwartz line. On electron microscopy, the Descemet's membrane can be divided into two distinct regions, an anterior 1/3 having a vertically banded pattern and the posterior 2/3 appearing amorphous and granular. The posterior surface of the Descemet's membranes and the periphery shows rounded warts-like escurrence called Hazel-Henle bodies, which increase with advancing age. Similar central excrescence known as guttatae are seen in Fuchs dystrophy. The last layer is endothelium. It consists of a single layer of flat polygonal or mainly hexagonal cells, which is seen in slit lamp microscopy appears as a mosaic shape. The cell density of the endothelium around 6000 cells per cube millimeter square at birth. In the human adults, these cells have hardly any ability to divide. The cells count falls by about 26% in the first year, and further 26% is lost over the next 11 years. Therefore, the increasing age number of cells is reduced to about 2400 to 3000 cells per millimeter square in young adults. The defect left by dying cells is filled by enlargement of the remaining cells. Hence, these cells vary in diameter from 18 to 20 mu early life to 40 mu or more in the aged. There is a considerable functional reserve for the endothelium. Therefore, corneal decomposition occurs only after more than 75% of the adult age cells are lost. The endothelial cells are best evaluated by specular microscopy. The endothelial cells are attached to the descendants membranes by hemidesmosomes and laterally to each other by their tight junctional complexes. The desmosomal linkages and zonulae occludence are continuous around the entire cell and thus close the intracellular space and the anterior chamber. This linkage is calcium dependent and plays an important role in maintaining the barrier functions of the endothelium. The endothelium also contains an active pump mechanism and is also involved in active secretions and protein synthesis. The high metabolic activity energy production for the above process by the endothelial cells is evidenced by the presence of abundant mitochondria, free ribosomes, rough and smooth surfaces, endoplasmic reticulum and Golgi complexes in the cytoplasm of the cells. In the eye, next to the photoreceptors, the endothelial cells contains highest number of mitochondria. The functions of the cornea. It is a powerful refractive lens. It transmits light in an orderly fashion. It helps the absorption of the drugs when applied in it. It protects the intraocular structures. The blood supply of the cornea. The cornea is a avascular structure. Small loops derived from the anterior ciliary vessels invade its periphery for about 1 mm and invade its nourishments. Actually, these loops are not in the cornea but in the some conjunctival tissues which overlaps the cornea. The nerve supply of the cornea. Cornea has rich supply of sensory nerve endings derived mainly from the long ciliary nerves, which are the branches of the nasociliary nerves. These long ciliary nerves, after arising from the nasociliary nerves, enters into the eyeball around the optic nerve along with the short ciliary nerves and run forward into the suprachoroidal space. A short distance from the limbus, these nerves pierce into the sclera to leave the eyeball, divides decomatously and connect with each other with the conjunctival nerves to form a pericorneal plexus of the nerves. About 60 to 80 myelinated trunks from the pericorneal plexus enters the cornea at the various levels via sclera, episclera and conjunctiva. After having gone for 1 to 2 mm in the stroma, the corneal nerves loses their myelin sheaths, branch decomatously and to form a stromal plexus. Although some nerves ends in the midstroma, most passes anteriorly and form a subepithelial plexus. The fibers from here penetrates the pores in the Bowman's membranes, lost their Schwab's sheath, divides into the filaments under the basal layer of the epithelium, which extends between the cells of all the layers of the epitheliums and from intraepithelial plexus. The nerves ends in the epitheliums are as fine beaded filaments. Thus, the cornea has an extensive innervational density which has a high near the center and gradually decreases towards the periphery. However, there are no nerves in the central posterior parts of the cornea, the Siemens membranes and endothelium. Thank you.